Hello friends, in this class we will start the queuing theory. We will do the introductory part first and then we will learn MM1 queuing model. What is queuing theory? So before that, what is a queue? A queue is a waiting line of customers. Okay, so in our daily life we find various queues at various places where the people wait for their service, because in queuing situations the valuable time of people or customers is wasted, energy is wasted. So minimization of queues or quick service provision of quick services is necessary. Therefore we need some mechanism to handle this chaotic situation of queues, and thus there is a theory like called queuing theory which helps us to answer certain questions regarding these queuing situations, like what will be the average weight of a customer in the queue and how many customers will be there in the queue or in a queuing system on an average. So that's why we study this queuing theory. But the study of queuing theory is totally based on a queuing system. Once a queuing system is defined, appropriate models can be mathematical or stochastic model can be made, and we can predict the behavior of the system to the maximum possible accuracy. What is a queuing system? A queuing system can be described as customers arriving for service, waiting for service if it is not immediate, and if having waited for service, leaving the system after being served. You can just see this diagram. This is diagrammatic representation of a queuing system. Customers arriving, okay, then there is a queue if they have to wait. Then there is a service facility where there are servers, and then the served customers which are leaving after getting service. So this whole thing is queuing system. Next is queuing theory. It is mathematical study of the behavior of queues. It consists of various mathematical models. The characteristics or elements or components of a queuing system. First of all, arrival process. Arrival process is normally random in nature, therefore it is necessary to know the probability distribution describing the time between successive arrivals, that is interval times. The customers may come one by one, or they may come in batches or bulk. So one should also know the probability distribution of batches of customers. Upon entering the system, a customer may exhibit three types of behaviors. Okay, one thing is that the customer will remain in the queue no matter how much time it takes for service. Okay, then in this case we can say the customer is quite patient. He has a lot of patience. But there are cases of impatience where a customer sees a long queue and decides not to join that system. So this behavior of customers is known as balking, whereas in some cases customers come and join the queue, but after some time they become impatient and leave the queue before getting service. This behavior is known as reneging. And another kind of behavior is where there are more than one queue, okay, in parallel. That is, a number of queues are operating in parallel. There are parallel servers, and the customer jump from one queue to another for getting quick service, or they jockey from one queue to another. This behavior is known as jockeying. Now the service process. The customers may be served one by one or in batches. The service times are often random in nature, so they should be described by appropriate probability distribution. Next is QDiscipline. It is the manner, it is the way in which the customers are selected for service. When a queue has formed, the most commonly used queue discipline is first come first serve. Some other queue disciplines are last come first served, service in random order, and priority schemes. We can see this last come first serve queue discipline in case of inventory stores where the items which are put first are taken out last. Okay, unloading of trucks, etc. There also we find these kind of systems. The service in random order, the systems where there is no order, okay, is maintained. Anyone can get service randomly. So the priority schemes are where the particular type of customers are given priority for service over the others. These are of two types: preemptive priority and non-preemptive priority schemes. Now coming to system capacity, the number of customers a system can accommodate is called the capacity of the system. That is the size of the waiting room. Okay, how much customers it can accommodate. Such queuing systems are of two types: finite capacity and infinite capacity. So most of the systems in our practical real life are finite capacity queuing systems, although there are cases where we find no restriction on the number of customers in the system. Okay, for example, open grocery shops, malls, the supermarkets, government hospitals, etc. etc. There is no limit on the number of customers. Those are known as infinite capacity queuing systems. Infinite capacity systems, no further customers are allowed when the capacity of the system is full. Okay, so this situation is just like forced bargaining. Now coming to next part, that is number of servers. The queuing systems may have a single server or a number of servers. There could be situations of multi-server systems like many servers and a single server queue, and many servers in parallel fed by many queues, that is a single server queue for each server. Kendall's notation of a queuing system. Okay, so this is represented by A, B, C, D, E, where A refers to interarrival time distribution, B service time distribution, C number of servers, D capacity of the system, and E queue discipline. Now coming to the first queuing model, that is MM1 queuing model. So this model is based on certain assumptions. Number one, arrivals to the queuing system occur one by one in accordance to a Poisson process of rate lambda. The interarrival times are independently, identically, and exponentially distributed with parameter lambda. The next assumption is there is a single server and the service times are independently, identically, and exponentially distributed with parameter mu. So Independently means there is no correlation between them, they are independent. The service time of one customer is independent of the service time of other customer. Identically means all these service times have the same type of distribution, probability distribution. Okay, so yes, the capacity of the system is finite. There is no restriction on the number of customers in the system. Number 4, the QDiscipline is first come, first served. That is, the customers are served in order of their arrivals. So now coming to formation of mathematical model. So for that, define P and T, the probability that there are n customers in the system at time T. So how do we proceed? Okay, we consider a very small time interval of length delta t, and we talk about the events occurring during this time delta t. Okay, and now we are interested in this probability p and t plus delta t. So at this time point t plus delta t, what is the probability that there are n customers in the system? Okay, so we will take different cases now. At time t, okay, let us say at time t there are n customers in the system, and during this time interval of length very small time length delta t, no arrival occurs and no departure occurs. So probability of no arrival in this very small interval of length delta t is 1 minus lambda delta t plus O delta t, and probability of no departure is 1 minus mu delta t plus O delta t. Okay, it is because of Poisson process. So plus Pn minus t. Okay, it means that at time t there are n minus 1 customers, and one customer arrives during this very small time interval and no departure occurs. So one customer arrives, this is the probability lambda delta t plus O delta t, where O delta t is a function which approximates all the higher order terms in delta t. So this is very small. So now this is the probability of no departure, 1 minus mu delta t O delta t. Okay, and according to Poisson process, no two or more events cannot occur during this time delta t. Yes, next is at time t there are n customers, n plus 1 customers, and during time delta t one departure occurs and no arrival occurs. No arrival and one departure. Okay, so one departure occurs, then it remains n after time delta t. So these are the possible cases, and therefore we further simplify the above equation like this, multiply the terms. So these underlined terms are simply underlined in order to show that these are higher order terms in delta t. So they will be approximated in O delta t. So they will go here. Okay, and these terms will remain, this and this. So in the next step, so P and T, just multiplying inside, P and T minus lambda plus mu delta T, P and T plus lambda Pn minus 1 T delta T plus mu Pn plus 1 T delta T plus O delta T. Now those underlying terms are all okay inside this O delta T. So just taking this P and T left side, so we have P and T plus delta T minus P and T, which is equal to minus lambda plus mu P and T delta T plus lambda Pn minus 1 T delta T plus mu Pn plus 1 T delta T plus O delta T. Dividing throughout by delta T, what we get? So this is delta t comes here, this with this cancel, this with this cancels, and this O delta t upon delta t. Now taking limit delta t tends to 0 throughout, so this becomes the derivative by definition. So this is ddt of p and t, and the right side, this is independent of delta t, this also. So these are simply written like this, and limit delta t tends to 0, O delta t upon delta t. Now this limit tends to 0 because now O delta t tends to 0 more rapidly as delta t tends to 0. So we are left only with this for n greater than equal to 1. So this equation, this differential difference equation is applicable for all n is equal to 1, 2, 3 and so on. But for n is equal to 0 we have to develop one more. So and p0t plus delta t, okay, now this probability is just p0t, no arrival occurs. There are 0 in the system, no arrival occurs and there is no point of departures because nothing is in the system, so that probability is not written. Yes, now p1t mu delta t O delta t means one departure occurs and 1 minus lambda delta t O delta t means no arrival occurs. So these are the possible cases for this. So this therefore this is equal to p0t, just multiplying inside p0t minus lambda p0 delta t plus p1, this multiplying this inside I get this is higher order term in delta t, okay. And in the next step p0t minus lambda p0t delta t plus mu p1t delta t plus O delta t, and taking this to left side, so we are getting this minus this is equal to minus lambda p0t delta t plus mu p1t delta t plus O delta t. Now dividing throughout by delta t and taking limit delta t tends to 0, so we get this. Again this tends to 0. Okay, so we are only left with dt of p0t is equal to minus lambda p0t plus mu p1t for n is equal to 0. So the equations 1 and 2 are the differential difference equations of the MM1 queuing model. In steady state as delta, now we are interested in steady state solution of this model, that is when time is very large. Okay. In that case, the system size probabilities, that is PNs, become stationary. Okay, the system behaves as it is under equilibrium, that is input rate is equal to output rate. So when the probabilities become independent, this derivative of constant dt of P and T, that becomes 0. Therefore, the equations 1 and 2 become like this. So this is independent of t, independent of t, and like this. So now we have to solve this in order to get the steady state probability. So from equation 4 we can have p1t in terms of lambda, mu and p naught, and then iteratively we will proceed with the help of equation number 3. So let us see what happens from equation number 4. P1 equal to lambda upon mu p naught. So from equation 3 we get mu pn plus 1 is equal to lambda plus mu pn minus lambda pn. Just interchanging the terms, and what we get, this lambda pn mu pn minus lambda pn minus 1 is equation number 6. Okay, now put n equal to 1 in 6, what we get, mu p2 equal to this one. So now this underlined portion, these two terms, these are equal to 0 because of equation 4. So therefore we have p2 equal to mu p2 equal to lambda p1. Therefore p2 equal to lambda upon mu p1, and p1 we have obtained in terms of p naught like this. So this will become lambda upon mu whole square p naught. Equation number 7. Okay, now put n equal to 2 in equation number 6. What do we get? We get mu p3 equal to lambda p2 plus mu p2 minus lambda p1. And again, because of 7, this is equal to 0. So we are left with p3 equal to lambda upon mu p2, and p2 we have already obtained. So just putting that value here, we are getting p3 equal to lambda upon mu cube p naught. So continuing in the same way, we will get Pn equal to lambda upon mu raised to power n p naught. So iteratively we reached at this Pn. Okay, now we will use the this normalization condition, that is the sum of all the probability equal to 1. So from 9, okay, just sum of this, and from 0 to infinity Pn, that is equal to 1, and it is again equal to P naught outside and inside lambda upon mu raised to power n, and if we expand this series it will be infinite Gp, and therefore its sum is first term upon 1 minus common ratio, that is lambda upon mu, and this will be convergent only if lambda upon mu is less than 1. So therefore P naught equal to 1 minus lambda upon mu, and for this holds only when this lambda upon mu is less than 1. So therefore, just substituting the value of P naught in that equation number 10, okay, we get equation, not equation number 10, but it is equation number 9 here. Okay, so we get lambda upon mu raised to power n 1 minus lambda upon mu, and lambda upon mu less than 1 and greater than equal to 0. So 11 provides the steady state probability equations, steady state probabilities, not equations, steady state probabilities of MM1 queuing model. Now measures of performance. First is average number of customers in the system or expected system size. So this is denoted by LS, and it is nothing but using the definition of expectation. It is n from 0 to infinity n into Pn. So just doing it, putting the values of this Pn and lambda upon mu independent 1 minus lambda upon mu independent of n. So we are left with n equal to 0 to infinity n into lambda upon mu raised to power n, and LS is equal to this one. If we say that this lambda upon mu is rho, okay, then we get this one. And now what is the sum of this? Let us say it is S. So just taking this S here, then doing rho times S, and then subtracting rho times S from S, we get this, and if we just find its sum, it will be rho upon this. So S is equal to rho upon 1 minus rho square. Just substituting here, I get LS is equal to rho upon 1 minus rho, or it can be written in terms of lambda upon mu like this. So lambda upon mu minus lambda. Average number of customers in the queue. So this can be obtained just like here, no, n minus 1 we will start from, because 1 will be in the server in a single server queuing system. 1 will be in the service, and n minus 1 will be in the queue. So average number of customers in the queue will be obtained by doing this, and from 1 to infinity n minus 1 Pn. Okay, so again just expanding the terms, multiplying inside. So just 1 to infinity and 1, this is 1 minus P naught, because if we include P naught here, it will become 0 to infinity, that will be 1. So from that we get this. This is n from 0 1 to infinity P naught. Pn is here, Pn equal to 1 minus P naught. So yeah, n is equal to this, and further, because this if I put 0 here, there will be if I put start this summation from 0, okay, what will happen? This term will be 0. So there is no problem if I start this from 0, because 0, when n is equal to 0, this term is 0. So this is same as that of this, right? And I can put the value of P naught. Okay, then yes, so this we have obtained earlier. You can see this is lambda upon mu minus lambda, and this we just obtained. So just simplifying, we get lambda square upon this one. And in terms of rho, I can see that you can say yes, it is we can do it just like here, and we get rho square upon 1 minus rho, right? So if we multiply inside, we get this. Okay, and average waiting time of a customer in the system, WS. WS is equal to LS upon lambda. So there is a formula like Little's formula or Little's law, which is this: L is equal to lambda WS. Average number of customers in the system is equal to average arrival rate into average waiting time of a customer in the system. So this one, from this formula we get ls, and ws is equal to this is the ls we have obtained and divided by lambda, so we get this one. So this ws is 1 upon mu minus lambda. And next is average waiting time of a customer in the queue. So wq is ws minus 1 upon mu. 1 upon mu is what? It is the average service time, or the service time of a customer in the queue. So just subtracting this, we get rho upon mu minus lambda, or in terms of lambda mu, it is lambda upon mu into mu minus lambda. This is my WQ. Thank you very much.